In a nutshell, this course is intended to be a shop class for computer science. Young computer science students are taught to drive the computer. But where do you go to learn what is under the hood? Trying to understand the operating system is unfortunately not as easy as just opening the bonnet. The current Linux kernel runs into the millions of lines of code. Add to that the other critical parts of a modern operating system: the compiler, assembler, and system libraries, and your codebase becomes unimaginable. Further still, add a university-level operating systems course, or four, some good reference manuals, 2 or 3 years of C experience, and just maybe you might be able to figure out where to start looking to make sense of it all. To keep with the car analogy, the prospective student is starting out, trying to work on a Formula One engine without ever knowing how a two-stroke motor operates. During their shop class, the student should pull apart, twist, turn, and put back together the two-stroke motor, and consequently have a pretty good framework for understanding just how the Formula One engine works. Nobody will expect them to be a Formula One engineer, but they are well on their way. Why from the bottom up? Not everyone wants to attend a shop class. Most people only want to drive the car, not know how to build one from scratch. Obviously, any general computing curriculum has to take this into account, else it won't be relevant to its students. So computer science is taught from the top down. Applications, high-level programming, software design and development theory, possibly data structures. Students will probably be exposed to binary, hopefully binary logic, possibly even some low-level concepts such as registers, opcodes, and the like at a superficial level. This course aims to move in completely opposite direction, working from operating systems fundamentals through to how those applications are compiled and executed. Enabling technologies. This course is only possible thanks to the development of open source technologies. Before Linux, it was like taking a shop course with a car that had its bonnet welded shut. Today, we are in a position to open that bonnet, poke around with the insides, and better still, take that engine and use it to do whatever we want. Everything is a file. An often quoted tenet of Unix-like systems, such as Linux or BSD, is everything is a file. Imagine a file in the context of something familiar like a word processor. There are two fundamental operations we could use on this imaginary word processing file. One, read it, existing saved data from the word processor. Two, write to it, new data from the user. Consider some of the common things attached to a computer and how they relate to our fundamental file operations. 1. The screen. 2. The keyboard. 3. A printer. 4. A CD-ROM. The screen and printer are both like a write-only file, but instead of being stored as bits on a disk, the information is displayed as dots on a screen or lines on a page. The keyboard is like a read-only file, with the data coming from keystrokes provided by the user. The CD-ROM is similar, but rather than randomly coming from the user, the data is stored directly on the disk. Thus, the concept of a file is a good abstraction of either a sink for or source of data. As such, it is an excellent abstraction of all the devices one might attach to the computer. This realization is the great power of Unix and is evident across the design of the entire platform. It is one of the fundamental roles of the operating system to provide this abstraction of the hardware to the programmer. It is probably not too much of a stretch to say abstraction is the primary concept that underpins all modern computing. No one person can understand everything from designing a modern user interface to the internal workings of a modern CPU, much less build it all themselves. To programmers, abstractions are the common language that allows us to collaborate and invent. Learning to navigate across abstractions gives one greater insight into how to use the abstractions in the best and most innovative ways. In this course, we are concerned with abstractions at the lowest layers, between applications and the operating system, and the operating system and the hardware. Many more layers lie above this, each worthy of their own courses. As these lectures progress, you will hopefully gain some insight into the abstractions presented by a modern operating system.